Cool, thank you. Just so I know what level to speak at, raise your hand if you know who Bach is. Great. Raise your hand if you know what a neural network is. Oh, this is the perfect crowd. Awesome. If you don't know, don't worry. I'm going to cover the very basics of both. So let's talk about Bach. I'm going to play to you some music. Now, what you just heard is what's known as a chorale. There are 4 parts to it: a soprano, alto, tenor, bass, playing at the exact same time. And there's very regular phrasing structure, where you have the beginning of a phrase, the termination of a phrase, followed by the next phrase. Except, that wasn't Bach. Rather, that was a computer algorithm called BachBot, and that was one sample out of its outputs. If you don't believe me, it's on SoundCloud. It's called Sample 1. Go listen for yourself. So instead of talking about Bach today, I'm going to talk to you about BachBot. Hi, my name is Feynman, and it's a pleasure to be here at Amsterdam. And today we'll talk about automatic stylistic composition using long short-term memory. So a bit of background about myself. I'm currently a software engineer at Gigster, where I work on interesting automation problems regarding taking contracts, dividing them into subcontracts, and then freelancing them out. The work on BachBot was done as part of my master's thesis, which I did at the University of Cambridge with Microsoft Research Cambridge. In line with the track here, I do not have a PhD, and I still can do machine learning, so this is a fact. You can do machine learning without a PhD. For those of you who just want to know what's going to happen and then get out of here because it's not interesting, here is the executive summary. I'm going to talk to you about how to train end-to-end, starting from dataset preparation all the way to model tuning and deployment of a deep recurrent neural network for music. This neural network is capable of polyphony, multiple simultaneous voices at the same time. It's capable of automatic composition, generating a composition completely from scratch, as well as harmonization. Given some fixed parts, such as the soprano line or the melody, generate the remaining supporting parts. This model learns music theory without being told to do so, providing empirical validation of what music theorists have been using for centuries. And finally, it's evaluated on an online musical Turing test, where out of 1,700 participants, only 9% are able to distinguish actual Bach from BachBot. When I set off on this research, there were 3 primary goals. The first question I wanted to answer was, what is the frontier of computational creativity? Now, creativity is something we take to be innately human, innately special in some sense. Computers ought not to be able to replicate this about us. Is this actually true? Can we have computers generate art that is convincingly human? The second question I wanted to answer was, how much has deep learning impacted automatic music composition? Now, automatic music composition is a special field. It has been dominated by symbolic methods, which utilize things like formal grammars or context-free grammars, such as this parse tree. We've seen connectionist methods in the early 19th century. However, they've fallen in popularity, and most recent systems have used symbolic methods. With the work here, I wanted to see, did the new advances in deep learning in the last 10 years, can they be transferred over to this particular problem domain? And finally, the last question I wanted to look at is, how do we evaluate these generative models? I mean, we've seen in the previous talk, a lot of models, they generate art, we look at it, and as the author, we say, oh, that's convincing, but oh, that's beautiful. And great, that might be a perfectly valid use case, but it's not sufficient for publication. To publish something, we need to establish a standardized benchmark, and we need to be able to evaluate all of our models about it so we can objectively say which model is better than the other. Now, if you're still here, I'm assuming you're interested. This is the outline. We'll start with a quick primer on music theory, giving you just the basic terminology you need to understand the remainder of this presentation. We'll talk about how to prepare a data set of Bach Chorales. We'll then give a primer on recurrent neural networks, which is the actual deep learning model architecture used to build BachBot. We'll talk about the BachBot model itself, the tips and tricks and techniques that we used in order to train it and have it run successfully, as well as deploy it. And then we'll show the results. We'll show how this model is able to capture statistical regularities in Bach's musical style, and we'll provide very convincing evidence that music theory does have empirical justification. And finally, I'll show the results of the musical Turing test, which was our proposed evaluation methodology for saying, yes, this model has solved our research goal. The task of automatically composing convincing Bach chorales is more closed than open of a problem as a result of BachBot. And if you're a hands-on type of learner, we've containerized the entire deployment. So if you go to my website here, I have a copy of the slides, which have all of these instructions. You run this 8 lines of code, and it runs this entire pipeline right here, where it takes the chorales, it pre-processes them, puts them into a data store, trains the deep learning model, samples the deep learning model, produces outputs that you can listen to. Let's start with basic music theory. Now, when people think of music, this is usually what you think about. You got these bar lines, you got notes, and these notes are on different horizontal and vertical positions. Some of them have interesting ties, some of them have dots. There's this interesting little weird hat-looking thing. We don't need all of this. We need 3 fundamental concepts. The first is pitch. Pitch is often referred to as how low or how high a note is. So if I play this, we can distinguish that some notes are lower and some notes are higher in frequency. And that corresponds to the vertical axis here. As the notes sound ascending, they appear ascending on the bar lines. The second attribute we need is duration. And this is really how long a note is. So this one note, these 2 notes, these 4, and these 8 all have equal total duration, but they're halvings of each other. So if we take a listen, the general intuition is the more bars there are on these ties, the faster the notes appear. With just those 2 concepts, this is starting to make a little bit more sense. This right here is twice as fast as this note. We can see this note is higher than this note. And you can generalize this to the remainder of this. But there's still this funny hat-looking thing. We'll get to the hat in a sec. But with pitch and duration, we can re-represent the music like so. Rather than representing it using notes, which may be kind of cryptic, we show it here as a matrix, where on the x-axis, we have time, so the duration, and on the y-axis, we have pitch, how high or low in frequency that note is. And what we've done is we've taken this symbolic representation of music, and we've turned it into a digital, computable format that we can train models on. Back to the hat-looking thing. This is called a fermata, and Bach used it to denote the ends of phrases. We had originally set out about this research completely neglecting fermatas, and we found that the phrases generated by the model just kind of wandered. They never seemed to end. There was no sense of resolution or conclusion, and that was unrealistic. But by adding these fermatas, all of a sudden the model turned around, and we found realistic phrasing structure. Cool. And that's all the music you need to know. The rest of it is machine learning. Now, the biggest part of a machine learning engineer's job is preparing their data sets. This is a very painful task. You usually have to scour the internet or find some standardized data set that you train and evaluate your models on. Usually these data sets have to be pre-processed and massaged into a format that's amenable for learning upon. And for us, it was no different. Bach's works, however, fortunately, over the years, have been transcribed into, excuse my German, Bach Werke Verdeschnix, BWV is how I've been referring to this corpus. It contains about all 438 harmonizations of Bach's chorales. And conveniently, it is available through this software package called Music21. This is a Python package that you can just pip install and then import it, and now you have an iterator over a collection of music. The first pre-processing step we did is we took the music, the original music here, and we did 2 things. we transposed it, and then we quantized it in time. Now, you can notice the transposition by looking at these accidentals right here, these two little funny backwards or forwards Bs, and then they're absent over here. Furthermore, that note has shifted up by half a line. It's a little hard to see, but it's happening. And the reason why we did this is we didn't want to learn key signature. Key signature is usually something decided by the author before the piece has even begun to compose. And so key signature itself can be injected as a pre-processing step where we sample over all the keys Bach did use. So we removed key signature from the equation through transposition, and I'll justify why that's an OK thing to do in the next slide. This first measure is a progression of 5 notes written in C major. And then what I did in the next measure is I just moved it up by 5 whole steps. So yeah, the pitch did change. It's relatively high, or it's absolutely higher on all accounts. But the relations between the notes didn't change. And the sensation, the motifs that the music is bringing out, those still remain fairly constant even after transposition. Quantization, though, however, is a different story. If I go back 2 slides, we'll notice quantization took this 32nd note and turned it into a 16th note by removing that second bar. We've distorted time. Is that a problem? It is. It's not perfect, but it's a very minor problem. So over here, I've plotted a histogram of all of the durations inside of the chorale corpus, and this quantization affects only 0.2% of all the notes that we're training on. The reason that we do it is by quantizing in time, we're able to get discrete representations in both time as well as in pitch, whereas working on a continuous time axis, now you have to deal, computers are discrete and are unable to operate on a continuous representation. It has to be quantized into a digital format somehow. The last challenge, polyphony. So polyphony is the presence of multiple simultaneous voices. So far, the examples that I've shown you, you've just heard a single voice playing at any given time. But a chorale has 4 voices: the soprano, the alto, the tenor, the bass. And so here's a question for you. If I have 4 voices, and they can each represent 128 different pitches, that's the constraint in MIDI representation of music, how many different chords can I construct? Very good, yes, 128 to the power of 4. That's correct. I put a big O because there's some you can rearrange the ordering, but more or less, yeah, that's correct. And why is this a problem? Well, this is a problem because most of these chords are actually never seen, especially after you transpose to C major, A minor. In fact, looking at the data set, we can see that just the first 20 chords, or 20 notes rather, occupy almost 90% of the entire data set. So if we were to represent all of these, we would have a ton of symbols in our vocabulary which we had never seen before. The way we deal with this problem is by serializing. So that is, instead of representing all 4 notes as an individual symbol, we represent each individual note as a symbol itself, and we serialize in soprano, alto, tenor, bass order. And so what you end up getting is a reduction from 128 to the 4th, all possible chords, into just 128 possible pitches. Now, this may seem a little unjustified, but this is actually done all the time with sequence processing. If you take a look at traditional language models, you can represent them either at the character level or at the word level. Similarly, you can represent music either at the note level or at the chord level. After serializing, the data looks like this. We have a symbol denoting the start of a piece, and this is used to initialize our model. We then have the 4 chords, soprano, alto, tenor, bass, followed by a delimiter indicating the end of this frame and time is advanced 1 in the future, followed by another soprano, alto, tenor, bass. We also have these funny-looking dot things, which I came up with to denote this little fermata, so that we can encode when the end of a phrase is in our input training data. After all of our pre-processing, our final corpus looks like this. There's only 108 symbols left, so not all 128 pitches are used in Bach's works. And there's about, I would say, 400,000 total, where we've split 380,000, or 380,000 into a training set, and 40,000 into a validation set. We split between training and validation in order to prevent overfitting. We don't want to just memorize Bach Chorales. Rather, we want to be able to produce very similar samples which are not exact identicals. And that's it. With that, you have the training set. And it's encapsulated by the first 3 commands on that slide I showed earlier, with BachBot, make dataset, BachBot, extract vocabulary. The next step is to train the recurrent neural network. To talk about recurrent neural networks, let's break the word down. Recurrent neural network. I'm going to start with neural. Neural just means that we have very basic building blocks called neurons, which look like this. They take a d-dimensional input, x1 to xd. These are all numbers like 0.9, 0.2. And they're all added together with a linear combination. So what you end up getting is this activation z, which is just a sum of these inputs weighted by w's. So if a neuron really cares about, say, x2, w2 will be 1, and the rest will be zeros. And so this lets the neuron preferentially select which of its inputs it cares more about and allows it to specialize to certain parts of its input. This activation is passed through this S-shaped thing called an activation function, commonly a sigmoid, but all it does is it introduces a nonlinearity into the network and allows you to be more expressive on the types of functions you can approximate. And we have the output called Y. You take these neurons, you stack them horizontally, and you get what's called a layer. So here I'm just showing 4 neurons in this layer, 3 neurons in this layer, 2 neurons in this top layer. And I've represented the network like this. Here we take the input x, so this bottom part. We multiply it by a matrix now because we've replicated the neurons horizontally. And when w's represents the weights. And we pass it through this sigmoidal activation function to get these first layer outputs. This is recursively done through all the layers until you get to the very top where you have the final outputs of the model. The w's here, the weights, those are the parameters of the network. And these are the things that we need to learn in order to train the neural network. Great. We know about feed-forward neural networks now. Let's introduce the word recurrent. Recurrent just means that the previous input, or the previous hidden states, are used in the next time steps prediction. So what I'm showing here is, again, if you just pay attention to this input area, and this layer right here, and this output, this part right here is the same thing as this thing right here. However, we've added this funny little loop coming back with, this is electrical engineering notation for a unit time delay. And what this is saying is, take the hidden state from time t minus 1 and also include it as input into the time t predictions. In equations, it looks like this. The current hidden state is equal to the previous inputs plus an activation of the previous inputs weighted plus the weighted activations of the previous hidden states. And the outputs is only a function of just the current hidden states. We can take this loop right here. Oh, sorry, before I go there. This is called a Elman-type recurrent neural network. This memory cell is very basic. It's just doing the exact same thing a normal neural network would do. It turns out there's some problems with just using the basic architecture. And so the architecture that the field has been converging towards is known as long short-term memory. It looks really complicated. It's not. You take the inputs and the hidden states, and you put them into 3 spots. Right here, the inputs, an input gate, a forget gate, and an output gate. And the point of adding all this complexity is to solve a problem known as the vanishing gradient problem, where this constant error carousel of the hidden state being fed back to itself over and over and over results in signals converging towards 0 or diverging to infinity. Fortunately, this is usually available as just a black box implementation in most software packages. You just specify, I want to use an LSTM, and all of this is abstracted away from you. Now, here, if you squint, you can kind of see that the memory cell that I've shown previously, where we have the inputs, the hidden states feeding back to itself to generate an output. I've abstracted that away like this, and I've stacked it on top of each other. So rather than just having the outputs come out of this H right here, I've actually made it the inputs to yet another memory cell. This is where the word deep comes from. Deep networks are just networks that have a lot of layers. And by stacking, I get to use the word deep inside of my deep LSTM model. But I'll show you later that I'm not just doing it for the buzzword. Depth actually matters, as we'll see in results. Another operation that's important for LSTMs is unrolling. And what unrolling does is it takes this unit time delay, and it just replicates the LSTM units over time. So rather than showing this delay like this, I've taken it and I've shown the -1th hidden unit passing state into the tth hidden unit, passing state into the t plus first hidden unit. Your input is of variable length. And to train the network, what you do is you expand this graph, you unroll the LSTM to the same length as your variable length input, and so in order to get these predictions up at the top. Great. We know all we need to know about music and RNNs. Let's move on to how BachBot works. To train BachBot, we apply sequential prediction criteria. Now, I've stolen this from Andre Karpathy's GitHub, but the principles are the same. Suppose we're given the input characters hello, and we want to model it using a recurrent neural network. The training criteria is, given the current input character and the previous hidden state, predict the next character. So notice down here I have H, and I'm trying to predict E. I have E, and I'm trying to predict L. I have L, and I'm trying to predict L. And I have L, and I'm trying to predict O. If we take this analogy to music, I have all of the notes I've seen up until this point in time, and I'm trying to predict the next note. I can iterate this process forwards to generate compositions. The criteria we want to use is, and so the output layer here is actually a probability distribution. Sorry, so I've taken the previous slide, and now I've put it on top of my unrolled network. So given the initial hidden state, which we just initialized all zeros because we have a unique start symbol used to initialize our pieces, and the RNN dynamics, so this is the probability distribution over the next state given the current state, so this yt is equal to that, and it's a function of the current input xt as well as the previous hidden states from t minus 1. We need to choose the RNN parameters, so these weight matrices, the weights of all the connections between all the neurons, in order to maximize this probability right here, the probability of the real Bach Chorales. So down here we have all the notes of the real Bach Chorales, and up here we have the next notes of those. In an ideal world, if we just initialize it with some Bach chorale, it'll just memorize and return the remainder, and that will do great on this prediction criteria, but that's not exactly what we want. But nevertheless, once we have this criteria, the way that the model is actually trained is by using the chain rule from calculus, where we take partial derivatives. Up here we have an error signal, so I know this is the real Bach note, the real note that Bach used, and this is the thing my model is predicting. Okay, they're a little bit different. How do I change the parameters? This weight matrix between the hidden state and the outputs, this weight matrix between the previous hidden state and the current hidden state, and this weight matrix between the hidden state and the inputs, how can I change those around? How do I wiggle those to make this output up here closer to what Bach actually had produced? Now, this training criteria can be formalized used by taking gradients, using calculus, and iterating in an optimization known as stochastic gradient descent. And when applied to neural networks, it's an algorithm called backpropagation. Well, backpropagation through time, if you want to get nitty-gritty, because we've unrolled the neural network over time. But again, this is also abstraction that need not concern you, because this is also usually provided for you as a black box inside of common frameworks such as TensorFlow and Keras. We now have the BachBot model, but there's a couple parameters that we need to look at. I haven't told you exactly how deep BachBot is, nor have I told you how big these layers are. Before we start, when optimizing models, this is a very important learning, and it's probably obvious by now. GPUs are very important for rapid experimentation. I did a quick benchmark, and I found that a GPU delivers an 8x performance speedup, making my training time go down from 256 minutes down to just 28 minutes. So if you want to iterate quickly, getting a GPU will save you will make you 8 times more productive. Did I just put the word deep onto my neural network because it was a good buzzword? It turns out, no. Depth actually matters. What I'm showing you here are the training losses as well as the validation losses as I change the depth. The training loss is how well is my model doing on the training data set, which I'm letting it see and letting it tune its parameters to do better on. And the validation loss is how well is my model doing on data that I didn't let it see. So how well is it generalizing beyond just memorizing its inputs? And what we notice here is that with just one layer, the validation error is quite high. And as we increase layers, 2 gets you down here, 3 gets you this red curve, which is as low as it goes. And if you keep going with 4, it goes back up. Should this be surprising? It shouldn't. And the reason why it shouldn't is because as you add more layers, you're adding more expressive power. Notice over here, with 4 layers, you're actually doing just as good as the red curve, so you're doing great on the training set. But because your model is now so expressive, you're memorizing the inputs, and so you generalize more poorly. A similar story can be told about the hidden state size, so how wide those memory cells are. How many units do we have in them? As we increase the hidden state size, we get performance improvements in generalization from this blue curve all the way down until we get to 256 hidden units, this green curve. After that, we see the same kind of behavior, where the training set error goes lower and lower, but because you're memorizing the inputs, because your model is now too powerful, your generalization error actually gets worse. Finally, LSTMs. They're pretty complicated. The reason why I introduced it is because it's actually so critical for your performance. The basic element-type recurrent neural network, where it just reuses the standard recurrent neural network architecture for the memory cell, is shown here inside of this green curve right here, which actually doesn't do too badly. But by using a long short-term memory, you get this yellow curve, which is at the very bottom. It's doing as best as out of all the architectures we looked at in terms of memory cells. Gated recurrent units are a simpler generalization of LSTMs. They haven't been used as much, and so there's less literature about them. But on this task, they also appear to be doing quite well. Cool. After all of this experimentation and all of this manual grid search, we finally arrive at a final architecture where notes are first embedded into real numbers, a 32-dimensional real, or vector rather, and then we have a 3-layer stacked long short-term memory recurrent neural network which processes these notes sequences over time. And we trained it using standard gradient descent with a couple tricks. We use this thing called dropout, and we drop out with a setting of 30%. And what this means is, in between subsequent connections between layers, randomly turn 30% of the neurons off. That seems a little bit counterintuitive. Why might you want to do that? It turns out, by turning off neurons during training, you actually force the neurons to learn more robust features that are independent of each other. If the neurons are not always reliably available, if the connections are not always reliably available, then then neurons may learn that to combine these two features and so you end up getting correlated features where 2 neurons are actually learning the exact same feature. With dropout, we will actually show on the next slide that generalization improves as we increase this number to a certain point. We also conduct something called batch normalization. It basically just takes your data and centers it back around 0 and rescales the variance so that you don't have to worry about floating point number overflows or underflows. And we use 128 time step truncated backpropagation through time. Again, another thing that your optimizer will handle for you. But at a high level, what this is doing is, rather than unrolling the entire network, which over the entire input sequence, which could be tens of thousands of notes long, well, not tens of thousands, thousands of notes long, we only unroll at 128, and we truncate the error signals. We basically say, after 128 time steps, whatever you do over here is not going to affect the future too much. Here's my promised slide about dropout. Counterintuitively, as we start dropping out or turning off random neurons or random neuron connections, we actually generalize better. We see that without dropout, the model actually starts to overfit dramatically. It gets better at generalizing, then it gets worse and worse and worse at generalizing because it's got so many connections, it can learn so much. If you tune dropout up to 0.3, you get this purple curve at the bottom, where you've turned it just to the right amount so that the features the model are learning are robust. They can generalize independently of other features. And if you turn it up too high, then now you're dropping out so much, you're injecting more noise than regularizing your model. You actually don't generalize that well. And the story on the training side is also consistent. As we increase dropout, you do strictly worse on training. And that makes sense too, because this isn't generalization. This is just how well can the model memorize its input data. And if you turn inputs off, you won't memorize as good. Great. With the trained model, we can do many things. We can compose, and we can harmonize. And the way we compose is the following. We have the hidden states, and we have the inputs, and we have the model weights. And so we can use the model weights to form this predictive distribution. What is the probability of my current note given all of the previous notes I've seen before? From this probability distribution, we pick out a note according to how that distribution is parameterized. So up here, this could be like, I think L has the highest weight here. And then so after we sample it, we just set xt equal to whatever we sampled out of there, and we just treat it as truth. We just assume that whatever the output was right there is now the input for the next time step, and then we iterate this process forwards. So starting with no notes at all, you sample the start symbol, and then you just keep going until you sample the end symbol. And in that way, we're able to generate novel automatic compositions. Harmonization is actually a generalization of composition. In composition, what we basically did was, I got a start symbol, fill in the rest. Harmonization is where you say, I've got the melody, I've got the bass line, or I've got these certain notes, fill in the parts that I didn't specify. And for this, we actually propose a suboptimal strategy. So I'm going to let alpha denote the stuff that we're given. So alpha could be like 1, 3, 7, the points in time where the notes are fixed. And the harmonization problem is we need to choose the notes that aren't fixed, or we need to choose the sequence x1 to xl, so we need to choose the entire composition such that the notes that we're given, x alpha, are already fixed. And so our decision variables are the things that are not in alpha, and we need to maximize this probability distribution. My kind of greedy solution, which I've received a lot of criticism for, is, OK, you're at this point in time, just sample the most likely thing at the next point in time. The reason why this gets criticized is because if you greedily choose without looking at what influence this decision now could impact on your future, you might choose something that just doesn't make any sense in the future harmonic context, but may sound really good right now. It's kind of like acting without thinking about the consequences of your action. But the testament to how well this actually performs is not how bad could it be theoretically, it's actually how well does it do empirically. Is it still convincing? And we'll find out soon. But before we go there, let's uncover the black box. I've been talking about neural networks as just this thing which you can just optimize, throw data at it, it'll learn things. Let's take a look inside and see what's actually going on. And so what I've done here is I've taken the various memory cells of my recurrent neural network, and I've unrolled it over time. So on the x-axis, you see time. And on the y-axis, I'm showing you the activations of all of the hidden units. So this is like neuron number 1 to neuron number 32. This is neuron number 1 to neuron number 256 in the first hidden layer. And similarly, this is neuron number 1 to neuron number 256 in the second hidden layer. Do you see any pattern there? I don't. I mean, I kind of do. I see there's like this little smear right here, and it seems to show up everywhere, as well as right here. But there's not too much intuitive sense that I can make out of this image. And this is a common criticism of deep neural networks. They're like black boxes, where we don't know how they really work on the inside, but they seem to do awfully good. As we get closer to the output, things start to make a little bit more sense. So I previously was showing the hidden units of the first and second layer. Now I'm showing the third layer, as well as a linear combination of the third layer, and finally the outputs of the model. And as you get towards the end, you start seeing, oh, there's this little dotty pattern. This almost looks like a piano roll. If you remember the representation of music I showed earlier, where we had time on the x-axis and pitch on the y-axis, this looks awfully similar to that. And this isn't surprising either. Recall, we trained the neural network to predict the next note given the current note, or all the previous notes. If the network was doing perfectly, we would expect to just see the input here delayed by a single time step. And so it's unsurprising that we do see something that resembles the input, but is not quite exactly the input. Sometimes we see multiple predictions at one point in time, and this is really representing the uncertainty inside of our predictions. So by representing the probability distribution, we're not just saying the next node is this. Rather, we're saying we're pretty sure the next node is this with this probability, but it could also be this with this probability, that probability. I called this the probabilistic piano roll. I don't know if that's standard terminology. Here's one of my most interesting insights that I found from this model. It appears to actually be learning music theory concepts. So what I'm showing here is some input that I provided to the model. And here I picked out some neurons. And oh no, these neurons are randomly selected. So I didn't just go and I fished for the ones that I looked at. Rather, I just ran a random number generator, got 8 of them out. And then I handed them off to my music theorist collaborator. And I was like, hey, is there anything there? And here's the notes he made for me. He said that neuron 64, this one, and layer 1 neuron 138, this one, they appear to be picking out perfect cadences with root position chords in the tonic key. More music theory than I can understand, but if I look up here, it's like that shape right there on the piano roll looks like that shape on the piano roll, looks like that shape on the piano roll. Interesting. Neuron layer 1, or neuron 151, I believe that is this one. A minor cadences ending phrases 2 and 4. No, that's this one, sorry. And again, I look up here. OK, yeah, that kind of chord right there looks kind of like that chord right there. Huh. They seem to be specializing to picking out specific types of chords. OK, so it's learning Roman numeral analysis and tonics and root position chords and cadences. And the last one, layer 1, neuron 87, and layer 2, neuron 37. I believe that's this one and this one. They're picking out I6 chords. I have no idea what that means. So I showed you automatic composition at the beginning of the presentation when I took some Bach music and I allegedly claimed it was Bach. I'll now show you what harmonization sounds like. And this is with the suboptimal strategy that I proposed. So we take a melody, such as this scale. We tell the model, this has to be the soprano line. What are the others likely to be like? This is what we get. Kind of convincing. It's almost like a Baroque C major chord progression. What's really interesting, though, is that not only can we just harmonize simple melodies like that, we can actually take popular tunes, such as this, generate a novel Baroque harmonization of what Bach might have done had he heard Twinkle, Twinkle, Little Star during his lifetime. Now I'm going off the track where it's like, oh, this is my model. It looks so good. It sounds so realistic. Yeah, but I was just criticizing that at the beginning of the talk. My third research goal was actually, how can we determine a standardized way to quantitatively assess the performance of generative models? For this particular task, and one which I recommend for all of automatic composition, is to do a subjective listening experiment. And so what we did is we built bachbot.com, and it looks like this. It's got a splash page, and it's kind of trying to go viral. It's asking, can you tell the difference between Bach and a computer? It used to say man versus machine. But the interface is simple. You're given 2 choices. One of them is Bach. One of them is BachBot. And you're asked to distinguish which one was the actual Bach. We put this out on the internet. We got around 1,900 participants from all around the world. Participants tended to be within the 18 to 45 age group. We got a surprisingly large number of expert users who decided to contribute. We defined expert as a researcher, someone who has published, or a teacher, someone with professional accreditation as a music teacher. Advanced as someone who has studied in a degree program for music, and intermediate as someone who plays an instrument. And here's how they did. So I've coded these with SATB to represent the part that was asked to be harmonized. So this is given the alto, tenor, bass, harmonize the soprano. This here was given just the soprano and bass, harmonize the middle 2. And this is compose everything. I'm going to give you nothing. This is the result that I've been quoting this entire talk. Participants are only able to distinguish Bach from BachBot 7% better than random chance. But there's some other interesting findings in here. Well, I guess this isn't too surprising. If you delete the soprano line, then BachBot is asked to create a convincing melody, and it doesn't do too well. Whereas if you delete the bass line, BachBot does a lot better. Now, I think this is actually a consequence of the way I chose to deal with polyphony, in the sense that I serialized the music from soprano, alto, tenor, bass. And so by the time BachBot got to figuring out what the bass note might be, it had already seen the soprano, alto, and tenor note within that time instant. And so it already had a very strong harmonic context about what note might sound good. Whereas when I got to the soprano note, BachBot has no idea what the alto, tenor, bass note might be, and so it's just going to make a random guess that could be totally out of place. To validate this hypothesis, which is work left for the future, you could serialize in a different order, such as bass, tenor, alto, soprano. You could run this experiment again, and you could see, and you would expect to see it go down like this if the hypothesis is true, and differently if not. Here I've taken the exact same plot from the previous plot, except I've now broken it down by music experience. Unsurprisingly, you kind of see this curve where people are doing better as they get more experience. So the novices are like almost only 3% better, whereas the experts are 16% better. They probably know Bach. They've got it memorized, so they can tell the difference. But the interesting one is here. The experts do significantly worse than random chance when comparing Bach versus BachBot bass harmonizations. I actually don't have a good reason why, but it's surprising to me. It seems that the experts think BachBot is more convincing than actual Bach. So in conclusion, I've presented a deep, long, short-term memory generative model for composing, completing, and generating polyphonic music. And this model isn't just like research that I'm talking about that no one ever gets to use. It's actually open source. It's on my GitHub. And moreover, Google Brain's Magenta project has actually integrated it already into Google Magenta. So if you use the polyphonic recurrent neural network model at Magenta in the TensorFlow project, you'll be using the BachBot model. The model appears to learn music theory without any prior knowledge. We didn't tell it, this is a chord, this is a cadence, this is a tonic. It just decided to figure that out on its own in order to optimize performance on an automatic composition task. To me, this suggests that music theory, with all of its rules and all of its formalisms, actually is useful for composing. In fact, it's so useful that a machine trained to optimize composition decided to specialize on these concepts. Finally, we conducted the largest musical Turing test to date with 1,700 participants, only 7% of which performed better than random chance. Obligatory note to my employer. We do freelance outsourcing. If you need a development team, let me know. Other than that, thank you so much for your attention. It was a pleasure speaking to you all.